Now let's imagine we had multiple classifiers, one for rain and one for whether the sprinkler is on or not. The rain classifier deals with features like wetness of the grass and thunder, whereas the sprinkler classifier deals with wetness of the grass, of course, but also whether or not one sees a hose on the ground. The probabilities for each of the classifiers work just like before. The probability of rain given W and T is the probability of W given R times the probability of T given R times P of R divided by the probability of W and T, which is essentially the probability of whatever evidence one actually observes, assuming one observes both these features. Similarly, we get the equation for the probability of a sprinkler given an observation of H and W. But W is the same observation. If we are observing W for this classifier, we should have the same value of W in this classifier. So we have to actually combine these networks into one network. And what we get is called a Bayesian network. Now, it's not a simple classifier. There are two things we could make conclusions about, sprinkler and rain, and some of the evidence is shared. Let's try to work out the probability for this network, starting with the joint probability of H, W, T, S, and R. Using Bayes' rule to factor R out, we get this first term. Then we factor S out. Again, we'll get H, W, T given S and R, and the probability of S given R, and the probability of R. This is simply a recursive application of Bayes' rule. We also know that S and R are independent. Whether or not the sprinkler is on or whether or not it had rained last night, we assume that these are independent. In practice, we might have some dependence. That is, one decides to put the sprinkler on only if it doesn't rain, but we ignore that for the time being. We also assume, as before, that the observations H, W, and T are independent given S and R. And this lets us factor this further as probability of H given S and R times the probability of W given S and R times probability of T given S and R, and because of independence of S and R, we get probability of S times probability of R. Now, this part is tricky. H and R are also independent because the probability of a hose lying on the ground doesn't depend on whether it's rained. The probability of thunder occurring certainly doesn't depend on whether the sprinkler has been put on. So these two terms can be replaced by the probability of H given S and the probability of T given R. As a general rule in a Bayesian network, and this is all you really need to understand or remember, all you need to deal with are the conditional probabilities of nodes given their parents. So we have H given S, T given R, and W given S and R because it has two parents. S and R don't have any parents, so they sit on their own as prior probabilities. So this basic Bayesian network equation gives us the joint probability. From this, one can compute whatever one actually requires simply using SQL by applying evidence, joining, and aggregating. Let's do a couple of examples. For example, we will ignore the hose and thunder and just deal with wetness, but now there are two possible causes for wetness: sprinkler being on and the rain being on. This is exactly what we started with, the confusing situation that classical logic had trouble dealing with, and let's see how probabilistic logic using a Bayesian network does better, perhaps. We have the conditional probability of W given S and R. Note that this is not the joint probability, so for any particular combination of S and R, these two rows for different values of W have to add up to 1, so 0.9 and 0.1, 0.7 and 0.3, 0.8, 0.2, etc. We also have the priors of probability that it rains in general and the probability that the sprinkler is on in general based on history. Let's write our joint distribution now. Probability of R, S, and W as probability of S and R given W times probability of W, and alternatively as probability of W given S and R times probability of S times probability of R, because we know that these two are independent. Given that the evidence that we see on the ground is the grass is wet, we can now say that the probability of R and S given W is the probability of W given R and S times probability of S times probability of R, and now we condition it by the evidence that the grass is wet, but we are only interested in the probability of R, so we sum out S. So now we're going to apply the summation operator in addition to the selection operator of W equal to S. Sigma, as before, is the probability or the inverse of the probability that W equal to S. Essentially, we get that simply by dividing by P of W in this equation. Convince yourself that this is the case, and let's see how one can execute this in SQL. Just like before, we select R, the sum of all the products of the P's from all the three tables, W equal to S, R equal to R, and S equal to S in all the tables. So I haven't written the full SQL over here, just have to make sure that all the common variables are equal and the evidence is applied. And we finally group by R, because we don't want anything to do with S. The results should have one row for every value of R. The result, it turns out, is the following. Let's look at the first row. We take the 0.9 from here, multiply it by the case where S equal to yes, because here S equal to yes, so we multiply by 0.3. There's another situation where S equal to no, where we also have rain equal to yes and W equal to yes, so that's 0.8, and that's multiplied by 0.7. Both of these are cases where rain equal to yes, so they're multiplied by 0.2 from this table, and we get 0.166. Similarly, in the case where rain equal to no, S equal to yes and W equal to yes, of course, 0.7 times 0.3, then we have 0.1 from this row, and S equal to no, so it's multiplied by 0.7, and of course both are the case where rain equal to no, so we multiply by 0.8. We get 0.224. Normalizing this so that the sum is 1, we get 0.166 divided by 0.166 plus 0.224 is 0.42. Or in other words, the expectation or the probability that the rain that happened last night, given that the grass is wet, is 42%. It's very important to note that earlier, when we just had rain and wetness and no sprinkler to talk about, we got a probability of 53% that it had rained if the grass was observed to be wet. Now, without knowing anything about the sprinkler being wet, being on or not on, simply the fact that there is a possible alternate cause for the grass being wet with an explicit probability table that it includes these, we get a lower value for the probability that it had rained. The fact is that given the fact that grass is wet, the probability that it had rained depends on whether or not the sprinkler was on. Even if we don't observe S, the fact that there's an alternate cause does change the probability from the situation where this node didn't even occur. Let's see that more explicitly now by seeing what happens if we do observe that the sprinkler is on.